Hello, AP Calculus students. Today's lesson is on differentiability. So we will be connecting differentiability and continuity and determining when derivatives do and do not exist. So first up we have a warm-up. I want you to pause the video, try this warm-up on your own, and then resume to see my solutions. So here's what I got right here. So this word differentiable, you should kind of see the root of the word derivative in there, right? Derivative, I don't know. It kind of sounds like derivative to me. So this is the ability to take the derivative, and it's showing that the derivative exists at a point. So if you came up with any idea like that, great job, you're on the right track. And then determining if f is continuous, this is a review problem, and we will be doing similar problems like this today. So this is a review problem from our lesson on continuity. So a reminder, in order for a function to be continuous at a point, f of a must equal the limit as x approaches a of f of x. So if this is true, then I know that f of x is continuous at x equals a. It's continuous at that point. So our function here, the only point where it might not be continuous is at this transition point, -1. So that is the point that we're looking at, where we're trying to figure out. So I found that f of -1 is -3. I found the limit from both sides, because that's where the issue would be if from the left and right, the left and right hand limits were different. But the limit from both the left and the right were -3, so I was able to give this final concluding statement that f of x is continuous because f of -1 equals the limit as x approaches -1 equals -3. So a little review of continuity. Here's the definition of differentiable. For a function f of x to be differentiable at a point a, f of a must be defined. Okay, so that point has to exist on the original function. And then down point 2, you should recognize that as the definition of the derivative. That's the definition of the derivative. So we can kind of summarize this as the left, oh no, that's the right hand, as the right hand derivative, which some teachers might say RHD, the right hand derivative equals the left hand derivative. Right? Which we would also call LHD. And then another shorthand way of writing this would be, because this is the derivative, we know that the derivative, one notation for that is f prime. So the derivative on the right hand side would be f prime of a from the right equals f prime of a from the left. And this is the notation that I like to use. I think it's the easiest. So as we approach that point, the derivative from both the left and the right hand side must be equal to each other. Okay, so this is kind of expanding upon point 1. So point 1 says that f of a must be defined. This is getting into that a little bit more. So if a point is not in the domain of f, then it is also not in the domain of f prime. So for instance, you can see I have 3 functions right here, f, g, and h. If I'm looking at the domains of these, I can see that the domain for f, x cannot equal 0 because I have a reciprocal function. The domain for g, this is a log, and I know that logs don't allow 0 or negative numbers into the argument. So I know that the x values here, x has to be greater than -1. So there's restricted domains. And then same thing for h. I can just see from my transition points right here. that the domain for h is x values greater than or equal to 0, because that's the only values there. So all three of these functions have limited, restricted domains, and so that means that the domain of f prime, the domain of the derivative, is also going to be restricted. So for instance, it wouldn't make sense for me to ask f prime of 0 because 0 is not in the domain. It wouldn't make sense for me to ask g prime of -1 because -1 is not in the domain. Alright? Etc., etc. So, let's do an example of this. Use the limit definition to determine the following. Is h of x, which is a piecewise function, differentiable at x equals 1? And again, we chose the point x equals 1 because that's the transition point. That's the point that is questionable. All the other points, I see that these are pretty basic. Those equations, those are very basic. I know I can take the derivative of a line, and I know I can take the derivative of a parabola. But I don't know if I can take the derivative at x equals 1, because that's where it transitions. So, we're going to find the left hand and the right hand derivatives. So I'm going to find the limit as x approaches 1 from the left of h of x minus h of 1 over x minus 1. So this equals 2x minus 2 times 1 all over x minus 1. Oops! I forgot my limit notation. Ugh, you all know I do this so much. So I need to I'm going to move this over. I'm going to scoot this over. I can't forget my limit notation. I might lose points on my AP exam if I forget this. Gotta keep writing it. So even if you're like Miss Patterson and you only remember at the end, make sure to always add that limit until we actually solve it. So I can see that if I try to plug in my point 1, if I try to plug it in, I'll get 0 over 0, which is an indeterminate form. So I can't take this limit yet. I've got to do some work on it. So I'm going to factor. I'm going to factor the numerator. And look at that. The x minus 1 clearly cancels out. That cancels out. And I'm just with, oopsies, I'm just left with the limit as x approaches 1 from the left of 2, which equals 2. Awesome. Alright, and now let's take the derivative from the right-hand side. So the limit as x approaches 1 from the right of h of x minus h of 1 over x minus 1. This time, since we're approaching from the right-hand side, we're going to use the other function. As x approaches 1 from the right, those are the x values that are bigger than 1. So we have x squared plus 1 minus 1 squared plus 1 all over x minus 1 equals the limit as x approaches 1 from the right. Let's do some simplification. This is x squared, 1 minus 1 minus 1 is minus 1. Cool. Again, if I tried to plug in 1, I would get 0 over 0, which is in indeterminate form. So I have to use my limit strategies. The first one being factor. So I'm going to factor the numerator again. X minus 1, x plus 1. And I can see, I'm right on the edge of the page. I can see that x minus 1 cancels out again. Whoosh, go away. And so I'm left with the limit as x approaches 1 from the right of x plus 1, which equals 2. So the left hand and the right hand limits are equal to each other. Therefore, h is differentiable at 1. Let's write that concluding statement. Let's summarize that up. So I can say that since, alright, f prime, it's not f, it's h. My function is h. Since h prime of 1 from the left equals h prime of 1 from the right, h of x is differentiable at x equals 1. So here's my gorgeous summary statement right there. This is a very common problem. Alright, let's keep moving on. Oh, I want you to go back and forth between these two and figure out how are these problems different. There's a tiny difference between them that changes the whole thing. And some of you might have noticed, in this problem, the second equation, x equals 1, but here, x never equals 1. And so this is a very sneaky problem where some people might immediately say, all right, let's find the left-hand and right-hand derivatives and see if they're equal to each other. But we'd have to realize that h of x is undefined at x equals 1. The original function is undefined. Therefore, h of x is not differentiable at x equals 1. Whoa, my handwriting is going to the garbage. And this is related to our definition, our first rule. So in order for f of x to be differentiable at a point, f of a must be defined. So since h of 1 is not defined for this function, then I know that it is not differentiable at x equals 1 either. Okay, let's do some more notes and kind of look at what differentiability looks like graphically. Okay, let's think about what differentiability looks like graphically. So a point fails to have a derivative at points where the graph has either a corner, cusp, vertical tangent, or discontinuity. So a corner is exactly what it sounds like. A corner looks like this. Kind of like an absolute value, or exactly like an absolute value. So if this is at -2, this would be the equation y equals x plus 2, the absolute value of x plus 2, and I would know that it is not differentiable at -2. So a corner is just like a sharp edge. Classic example is an absolute value. You could also get sharp edges from piecewise functions. A cusp looks like this, kind of like a corner, except not straight lines. And I'm going to, actually going back to this corner, I do want to say the way to quickly prove, this is not differentiable, is really easy with corners because it's linear functions. So I can just say, the slope here is -1 and the slope on the right hand side is 1. So with linear functions it's super easy to find the slopes and just say, yeah, the slope on the left does not equal the slope on the right. Or the derivative on the left does not equal the derivative on the right. It'd be a little bit harder to prove with a cusp because cusps are curvy. So we would need an actual equation. We would need an equation, not just the graph, in order to figure out the slope on the left and the right, the derivative on the left and the right. But the types of equations that make cusps look like this. Those types of equations make cusps. And obviously they're not differentiable at the point right there. Vertical tangents are, again, exactly what they sound like. They're equations that start going vertical for a period of time. So I can see here at 0, the tangent line is completely vertical. And remember, vertical lines have a slope that is undefined. Vertical lines have undefined slopes. So that is why vertical tangents are not differentiable, because it's the slope is undefined there. And the types of equations that make vertical tangents look like this. Like that. Okay, and then discontinuities. Well, you know what discontinuities are. Discontinuities include jumps, holes, vertical asymptotes. So, if a function is not continuous, it is automatically, my spelling, if a function is not continuous, it's automatically not differentiable. So, I could draw any sort of discontinuity. We'll just draw it like this. So I see that it is not differentiable here at 0. Because the left and the right derivatives, not the same. And it's just not continuous. Okay. Cool. I will make a note. So functions that are continuous, or functions that are smooth. And I know this seems like a weird way to describe a function, but ones that are smooth, like a polynomial, so all polynomials are differentiable. These are the ones that are differentiable. Differentiable. Whew, tough word to spell. But if they're smooth, so if they don't have like a corner, cusp, vertical tangent, or discontinuity, then they're differentiable. So this includes all lines, all polynomials, logs, exponents. Those are nice smooth functions. And then finally, this is your last set of notes before our examples. Just comparing the relationship between differentiability and continuity. This is the very formal way of writing it. That formal definition is the same as this. So if a function is differentiable at x equals c, then it is definitely continuous. So differentiability implies continuity. Okay? If it's differentiability, it's automatically continuous. Kind of in contrast, it is possible for a function to be continuous at x equals c and not differentiable. So continuity does not imply differentiability. And the greatest example of that is the absolute value. Right? We just looked at that. The absolute value looks like this. It is continuous, but it is absolutely not differentiable because it has a corner. So that is the best counterexample to that. All right, let's look at some notes. So here are a bunch of graphs, and we need to determine if these graphs are continuous, differentiable, both, or neither at the given point. So the first two, A and B, those are not continuous. They're just absolutely not continuous. They've got a jump and a hole. So if it's not continuous, it's automatically not differentiable because right here, if there's a discontinuity, it fails to have a derivative. So these two are neither. Can you see any other graphs that are like A and B that are neither because they are not continuous? Do you see any other ones like that? Correct, E. E has a vertical asymptote that is not continuous, which means it's not differentiable. So those three are neither. The rest of these are continuous. Now let's decide if they're differentiable. C. Ooh, this is nice and smooth. No corners, no cusps. This is both. It's continuous and differentiable. D, it might be hard to see, but if we go from the left, this is a straight line, and then from the right, it's like a curve. That results in a corner. This has a corner, so the D is continuous, but it is not differentiable. Same thing with f. This kind of looks like a compressed absolute value. This is continuous, but it's not differentiable because it has a corner. So I'll really emphasize there's a corner there, there's a corner there. What about g? Yeah, g also has a corner. So g is continuous but not differentiable. Finally, h. H is a little tricky because it does look smooth, right? That looks super smooth, but this has a vertical tangent. I should draw it in red to make it stand out. This is a vertical tangent right here. So at the vertical tangent, it is not differentiable, which means this one is also only continuous. It's not differentiable. So the only function that was both differentiable and continuous is c. Okay, we're going to move on to our final example. So determine if the functions are continuous or differentiable at the transition point. So often this is going to happen at on the AP exam where you have to determine both continuity and differentiability. So continuity, we'll start with continuity here. We have to check the limits of the function from the left and the right. So we have to figure out, does the limit as x approaches 2 from the left of f of x, does that equal the limit as x approaches 2 from the right of f of x? So this is the limit as x approaches 2 from the left. We'll use the bottom equation because those are the x values smaller than 2. And this is what we're checking. So we don't know. I'm going to put a little question mark. We don't know. We're checking this. And then the limit as x approaches 2 from the right of f of x, we'll use the top equation. Like that. Whew, okay, let's plug in 2. So we have 4 minus 2 on the left, and we have 2 squared minus 6 times 2 plus 10. I'm going to do a little mental math. So this is 2 equals 4 minus 12 is negative 8 plus 10 is 2. It is continuous. So it is continuous. Good. I'm like running out of space. So I'm gonna give you a little help. So instead of using the definition of the derivative, I'm just gonna tell you what the derivative is. I'm gonna be nice and just tell you what the derivative is. Here it is. You'll be able to do it that fast very soon as well. And so, in order to check differentiability, I'm going to so run out of space. Let's see if I can move this up just a tiny bit. Can I make it smaller? No. Just got to move it up a bit. Give me a little bit more room. Okay. So differentiability, I have to check, does the limit of as x approaches, oh no, sorry. We don't have to do the limit anymore because I already found the derivative for you. So does f prime of 2 from the left equal f prime of 2 from the right? So f prime of 2 from the left, we'll use the bottom equation, which is negative 1. F prime of 2 from the right uses the top equation, so that's 2 times 2 minus 6. Ooh, this doesn't look like it works. So negative 1 equals 4 minus 6 is negative 2. Let's write our quick summary statement. I'll write it in red. So for this function, f of x is continuous but not differentiable at x equals 2. So in order to write the summary statement, we do have to make sure we show all this work. We do have to show the work, and we do have to use proper notation. Okay, part B. Ooh, this B equation looks familiar. We already proved that this was continuous. This is the same problem from the warm-up. So I do know, right? It is? I think it is. Yeah, it is. Okay. So it is continuous because they both equal 3. Awesome. Save us some work. So I know that, what is it? The limit as x approaches -1 from the left of f of x equals the limit as x approaches -1 from the right of f of x equals -3. So it's continuous. So we still need to write, even though we did the work, we still need to show this summary statement to say like, ooh, yes, this is continuous. And then let's check differentiable. I'm just saying continuous and differentiable like this. So checking differentiability. I'll give you f prime again. So f prime of x equals 2x plus 1 for x greater than or equal to -1, and it equals -1 when x is less than -1. So let's check this f of x. F prime of -1 from the left equal f prime of -1 from the right. This is what we're checking. So f prime of -1 from the left, we'll use the bottom equation, -1. And f prime of -1 from the right, we'll use the top equation. -1 does indeed equal -1. So this one is also both continuous. Oh no, this one is a little different. This one is both continuous and differentiable. So here we would say f of x is both continuous and differentiable at x equals -1. Amazing. Very cool.